Hi, my name is Ryan Meyer. I'm a technical marketing engineer here at Dell Technologies. Over the course of this video, I'll be showing how PowerStore Metronode delivers Metro active-active capabilities both during a disaster and without any impact to the data path. PowerStore Metronode showcases the full potential of a Metro configuration, a truly disaster-resilient architecture which enables business continuity without the need for user intervention. Now, before I get into the demonstration, first let me explain a little bit about what a Metronode configuration looks like. Using two sites within Metro geographical boundaries, volumes are paired up across both sites and presented as a single virtual volume to the host. Think of this virtual volume as having two legs which are identical, always have active read-write access, and always syncing with each other. In the event of a failure on Site 1, the Site 2 leg has an identical copy and remains continuously available to the host. From the host perspective, there is no loss in connectivity to the volume, and there is also no data loss or recovery actions needed. By installing a witness server on a separate fault domain, you are also protected from any split-brain scenarios that can happen when one Metronode loses connectivity to the other. This allows failover to happen automatically and seamlessly without any user intervention. Likewise, when a site becomes available again, Metronode automatically recovers and continues syncing your data. The last thing I want to mention before we continue is that Metronode has zero performance impact on your storage. Because we are truly active-active, there is no hidden cost or overhead like you would have with a pseudo-Metro or active-passive configurations. With Metronode, you are getting the full potential of each storage system with nothing left waiting on standby. In a few seconds, I'll walk through provisioning a virtual volume using Ansible playbooks and continue through simulating what a disaster scenario would look like from an administrative point of view. Before we begin, let's briefly review what our Metronode environment looks like. On the left side of the topology chart, we have Site 1 using a PowerStore 3000T as the underlying backend storage. This is connected through the SAN fabric to the Metronode. On the front end, we have a VMware ESX cluster hosting our virtual machines. On the right side of the topology chart, we have a very similar configuration, except we are instead using a PowerStore 1000X as the underlying backend storage. That's right, Metronode works seamlessly with heterogeneous storage. In fact, you can mix different storage products, like a Dell EMC Unity XT on one site and a PowerStore on the other. Now, in the middle of the chart, we have our virtual machine clients, which are presented with virtual volumes. Behind the scenes, the virtual volumes have a leg at each site, which is always synced, but from the host perspective, this just shows up as a single volume. Metronode also works on a granular workload selection. This allows you to select which volumes you want to use Metro capabilities for and which you do not. You are not forced to go all or nothing. This helps minimize cost and negates the need to have identical system types at each location. Using Ansible, we can automate the provisioning process of a virtual volume. As you can see here, we first create the underlying volumes from the Site 1 and Site 2 PowerStore systems. Then, these are discovered by the Metronode and configured into a single virtual volume, stretching across both sites. Finally, the virtual volume is then presented to the specified VMware cluster. As you can see, by using Ansible, this whole provisioning process took all of about 15 seconds to complete. Now let's take a look at the Metronode interface and check the status of the virtual volume that was just created. By selecting our distributed storage, we can click on our virtual volume and then see a visual map. This map shows the underlying storage and also lets us know that each leg of the virtual volume is up and running. Now, I've already gone ahead and presented the virtual volume as a raw device map to a virtual machine within the ESX cluster. As you can see, I've also started running a workload on it using VDBench. Switching over to PowerStore Manager, we can also take a look at each storage system. On the PowerStore 3000T, we can see that I/O is running on the first site leg. And if we switch and look at the PowerStore 1000X, we can also see that I/O is running on the second leg. This indicates that we have a truly active-active configuration. Now that we have a virtual volume presented and a workload running on it, let's see what happens when a natural disaster occurs. In this example, I've simulated a disaster by removing network connectivity from the PowerStore on Site 1. This could happen in many ways, such as something minor like an unexpected maintenance window, or even something as critical as a total site loss due to natural disaster. Whatever the scenario is, if we come back to our Metro node interface, we can see that the Site 1 cluster is now showing a failure. If we navigate to our virtual volume, we can also see that there is a failure on the volume itself. By looking at the map of the virtual volume, we see that we've also lost one of the underlying legs of storage. However, by inspecting the remaining leg, we can see that the service status is running and the device is still functioning normally. Switching to the PowerStore 3000T, which is the storage on the site that lost connectivity, we can see that the I/O dropped to 0 as expected. Now looking at the PowerStore 1000X, which is the remaining leg of the storage, we see that I/O is still carrying on and did not get interrupted or dropped. We also saw some additional write activity, but this is expected as the second leg is now taking on all of the I/O. Lastly, if we take a look at our virtual machine, we see that the volume has remained connected and the workload is still running normally. There are no errors or timeouts. Let's review what we've learned from this disaster scenario. With the PowerStore Metro node configuration, we've witnessed a true active-active volume that was continuously available even in the event of a disaster. With this means our recovery time objective, or how long it took to recover, and our recovery point objective, or how much data was lost after recovery, are both 0 because there was no loss in connectivity and no need to restore from a backup. Likewise, our decision time objective, or the time needed to make a decision to failover, is also 0, because the failover process was automatic and no user intervention was needed. So with PowerStore Metro node, you can deliver truly active storage resources to your data centers that are both continuously available and have seamless failover capabilities. That's it for this video, and I hope you enjoyed watching.